Okay, so let's look at what I think we can consider sort of the standard projectile motion situation, where we have a coordinate frame we set up that's horizontal and vertical. So we'll set up x like that, y there. We have acceleration due to gravity going downward. So there's our gravity acceleration vector. And we've got an object fired at a speed of v0 and an angle theta. So what we have here, then, we can start from accelerations. We can say the acceleration in the x direction equals 0 because gravity is just pointing straight down. It's not affecting us in the x direction. A sub y is negative g, and then our initial x velocity is going to be this speed v0 times the cosine of theta. V0 times, let me try the eraser here and see how this works. Let's try the eraser. Alright, eraser. Okay, so v0x equals v0 times cosine theta, and then v0 in the y direction equals v0 sine theta. Okay, finally, our initial positions, x0, well, we chose the origin to be the starting position of the object, so conveniently x0 and y0 are both equal to 0. So, setting up our equations of motion is very easy, so I'm going to write, just for reference here, I'm going to write x equals x0 plus v0 t plus 1/2 a sub x t squared. But in fact, a lot of these are going to vanish or cancel out to something else. So excuse me, v0 in x. There we go. So let's look at this. X equals, and we started at 0, so there's no term there. And then the v0 x term, well, v0 x is just v0 cosine theta, right? So equals v0 cosine theta times t, and there's no acceleration term for x. So this here is our entire x position equation. Y equals, again, y0 is 0. The initial velocity in the y direction is v0 sine theta times t, and then that's minus 1/2 g t squared. Okay, and there's our y position equation. For velocities, v sub x equals v0 cosine theta, which is our initial x velocity, right? So this is, for the reference equation here would be v sub x equals v0 x, well, and I don't have space to write in the rest, but plus a sub x times t, if you'll recall. So this is, this is like continuing this line here. But there is no a acceleration in the x direction, so vx equals v0 cosine theta. That's all she wrote for velocity in the x direction. Velocity in the y direction is the initial y velocity, which again we have here. So is v0 sine theta, and then that's plus acceleration in the y direction times t. Acceleration in y is negative g, so that goes minus gt. Let me polish off the theta there. So, and that is our velocity y equation. We already know if we want accelerations down here, we already know that acceleration in x is 0, acceleration y is, okay, let's get the eraser again and see how well that works. Hard eraser. Oh, I like this eraser thing. Okay, back to our pen. Alright, so acceleration in y equals negative g. So there we go, and now we're all set. So, what do we want to know about this whole situation here? Because we've basically done all the equations of motion, so what do we want to know? One thing I'd like to know is how long it stays in flight. So let's find what the time is when it hits the ground. Time t, I-M-E. What was that thing? I don't know. So time of impact. So what's a condition that gives us impact? Well, that's when this thing hits the ground again, right? So y equals 0 is what's, when that's true, y is equal to 0 again. So we can then plug that into our y position equation up here. So that's going to equal v naught sine theta times t minus 1/2 gt squared, and that all equals 0, right? So what that gives us then is that, right, 1/2 gt squared equals v naught sine theta times t, which then gives us two answers. It gives us t equals 0 as one answer, because if both the t is 0, then this and this are both 0. And the other answer it gives us is that t equals 2 v naught sine theta over g. And that's the time it takes, that's the time it's in flight. So that's the time of flight, right there. And then, how far does it go, before it hits the ground? How far does it fly through the air? Distance of impact is what I'm trying to write there. So, we take this time here, and, this time here, I'm going to plug that into our x equation. So, x at impact equals this equation evaluated at t equals this. So, that's going to equal v naught cosine theta times 2 v naught sine theta, and this one is over g. So x at impact then equals 2 v naught squared over g times cosine theta times, well, no space for that, times sine theta. So let me actually just scroll this down a little, and I can try to write again that, let's see, where are we? So there we go. We can say x equals 2 v naught squared over g sine theta cosine theta. And this is v naught squared. Still not thrilled with the way this pen works on this thing. I don't know. And so that then, is an equation, is a relationship that tells how far this object flies while it's in the air. So that's kind of useful. Suppose now we have, suppose we want to maximize that x. Maximize distance flown. Well, what can maximize x? Let's assume that we've got sort of a one gun or one throwing arm or whatever it is. So our v naught is fixed. We can't make that go any harder without spending a lot of time in the gym working out or buying a bigger gun or whatever. And we know what planet we're on. We're on Earth. Units you're using, so g is going to be stay the same. So all we really have to play with here is this angle theta, which is the launch angle we have. So what angle theta will give us the maximum distance of flight, maximize x? And the answer, which unfortunately I can't show you without calculus, the answer is theta equals 45 degrees. And if your launch angle is 45 degrees, you'll go this far, say. And you can sort of imagine, that'll give you, let's see, well, if theta equals 45 degrees, then what you'll get is x equals, and then sine theta and cosine theta. Well, sine theta is root 2 over 2. Cosine theta is square root of 2 over 2. So together, those equal 1/2 times the 2. So x there is just going to equal v naught squared over g. Okay. Let's see if we do 2 a little better there, maybe. I don't know. So you can imagine if you're at 45 degrees, if you launch at 45 degrees, it'll go this far. There's our ground. If you launch at some higher angle, then you'll go up higher, but you don't have nearly as much horizontal velocity to begin with. So you end up splashing down, well short. And if you launch at some lower angle, well, you're going faster horizontally, but you don't get much altitude. So you'll also hit the ground like that. So 45 degrees is the angle that gets you the furthest, the longest distance. You can't prove it without calculus, but it's something I think a lot of us sort of know more or less intuitively. If you have to throw a ball to someone, and they're a certain distance away, and you want to sort of minimize the effort you have to put into throwing it, you try to launch it at an angle of about 45 degrees.